The way to find out is to do an experiment. Here we've got two parallel metal plates. The top one's connected to the top of the Van de Graaff generator and the bottom one's connected to the base. Turning the generator on will set up an electric field between the plates, a uniform field. Now in this case I can also measure the electric field. It's a slightly indirect method. I've put the bottom plate on a balance. At the moment there's no field, and so the balance is just reading the weight of the bottom plate. If there was a field, there'd be a force of attraction between the plates and the balance reading would change. And from that change, the field can be deduced quite simply. It's displayed on the meter over there. At the moment it's reading 0 because there's no field. Now, I'll try and establish a field of 1 kilovolt per centimetre. Only one division, about there. But nothing's happening. No spark, no breakdown. I'll increase the field a little. 2, nothing happening. 5, still no effect. Keep on going up. 15. There we are, a spark. Do it again. That happened at about 28 kilovolts per centimetre. And that's a field 28 times greater than apparently exists within thunderclouds. In fact, if I was doing this experiment under ideal conditions, with dry air and completely flat plates, I'd expect an even higher breakdown field, about 30 kilovolts per centimetre. That's 30 times greater than that which exists in thunderclouds. So we have a problem. Why does the air in thunderclouds break down if the field isn't large enough to cause breakdown? How do we bridge that factor of 30? Well, for a start, the lower air pressure in a cloud high above the ground reduces the breakdown field, but only by a factor of 2. And a factor of 2 isn't a factor of 30. We need some other effect. Now, could this be provided by the water drops in the thundercloud? Water's a fairly good conductor, and so, in effect, we've got lots of tiny conductors in the cloud. Do these conducting spheres of water affect the 1 kilovolt per centimetre electric field? An easy way of finding out is by doing a low voltage experiment, using, in fact, your home kit apparatus.
You've seen a very similar setup to this before. 0 volts on one plate, 5 volts on the other. I can measure the potential at any point, and the value is shown on this meter. I could also follow an equipotential, say the 2 volt one. And as we'd expect, it's parallel to the electrodes. In fact, all the equipotentials are parallel and equally spaced because the field is uniform. And of course the field lines are perpendicular to the equipotentials. Now let's see how the field would be modified in the presence of a spherical drop of water. I'm going to model that in my two-dimensional experiment by this conducting disc. Let's try and follow the same 2 volt equipotential. As we'd expect, it's distorted in the region of the disc. I could repeat that process for other equipotentials, building up a whole family of curves and the corresponding electric field pattern. A good way of looking at this pattern is to think about the charges, positive on one electrode, negative on the other. These will induce charges on the disc, and where these induced charges are concentrated, the field lines are deflected and the spacing of the equipotentials decrease. The disc enhances the field. If we were to carry out a three-dimensional experiment, we'd find that there were regions close to a spherical water drop where the field is enhanced by a factor of about 3. Steve already said that the reduced pressure also causes an enhancement by a factor of about 2, so we've got a possible 6-fold increase overall. But this still falls far short of our original requirement of a 30-fold enhancement. So according to this low voltage experiment, spherical water droplets don't seem to make nearly enough difference.
Well, let's see if they do in a high field experiment. I've just put a small drop of water into the gap between the plates. When I turn on the field, we'll be able to see what effect it has on the breakdown. Remember, before I was able to apply a field of about 28 kilovolts per centimetre before anything happened. Now, watch the drop very closely. Now, there's something rather interesting happening. The water drop is being distorted by the field, pulled into a point. If I go on, the pointed drop is discharging the plates, just as the pin did earlier. It's quite a complicated process. Now let's see it again more slowly. I'll freeze it there. As the field increases, the drop becomes more pointed. Charge is being pulled through the water into the top, causing a local enhancement of the electric field. Even with a fairly low applied field, the field at the top of the drop is sufficient to cause breakdown. The plate discharges quickly, this time with a spark, and the water drop is pulled back by surface tension. I'll start the motor going and you'll be able to see the whole process happening repeatedly. But now, because the applied field is greater, the conditions are right for sparks to be produced, but at a much lower average field between the plates than before without the water drop. Now, this is a crucial observation. The enhancement of the electric field due to the concentration of charge at a point is important in many applications. And in the context of lightning, field enhancement near water drops is able to cause breakdown, even though the overall electric fields in the thunderclouds are quite low. But there's one more problem. How does a localized breakdown such as this grow into the full splendor of a lightning flash? To find out, it's necessary to look more closely at what's involved in the breakdown of a gas at a microscopic level. Gases are normally insulators. They consist of uncharged molecules. But occasionally, a cosmic ray or an energetic particle from some radioactive event will strike an atom and ionize it, freeing an electron and leaving a positively charged ion. If there's an electric field present, the electron will be accelerated by the field. The positive ion, being much more massive, will accelerate much more slowly, and of course in the opposite direction to the electron. However, this sort of event is very rare, so the currents produced by this primary ionization are absolutely tiny. As we know, gases are usually insulators. But the result of primary ionization is rather different if the electric field is very large. Then the electron will accelerate very rapidly, acquiring a lot of kinetic energy. And if a very energetic electron collides with an atom, the atom may be ionized, releasing another electron. There's another possibility. Some of the energy of the free electron may be transferred to a second atom without ionizing it. This atom later sheds the excess energy by emitting light, and this light may be able to ionize yet another atom, leaving two free electrons. That's called photoionization.